All right. I think we are back. There we go. Yeah, it turns out like people in class sometimes want to talk about things and they want to talk about things off stream. So we talk about things off stream. I gave away the answers to everything in the module if you showed up in person today. All right. Big L for all of the Twitch viewers. Okay. I didn't really do that, but it'd be funny if I did. So, today is October 10th, 2024, here at CSE466. We are wrapping up, hopefully, dynamic allocator misuse or how we can exploit the heap. I am Robert Washington, and today again, I have no camera. We'll try and have that fixed at the other side of fall break. Memes. This is not related to the course. I just thought it was a great meme. For those that are unaware, I'm the one that manages the Twitch and YouTube channels for us. So I get the pleasure of choosing what is our wonderful thumbnail. And somebody made a nice D&D alignment chart of it because it turns out we're kind of inconsistent. If somebody has an opinion on like what they think is the best, I like smiling faces. I like chaotic good over there the most personally. Let me know. If it's not a major amount of effort, I'll definitely consider it. Memes about memes. So one of the things that I did was in theory, made extra credit live on the grades page, and people were initially happy until they looked at their grade, and then they were like, wait a minute, you're taking away a week of memes." So there are people who are claiming that somewhere at some point I said memes start on Monday. Maybe I did, maybe I didn't. I'm not saying that I didn't say it. I'm saying that I don't recall saying it. So if somebody does the archaeology there to find where I said it on stream, we'll address it then. In the meantime, I don't really want to change grade related stuff willy nilly. So I'm going to leave it as is until we have a permanent solution. That is my general stance. But I definitely understand if you feel like you took a hit there. Better to find out now than at the end of the semester, I suppose. So the live grading is doing what was intended, right? You have a better idea of what's actually happening to your grade. Apparently, I'm the nice mean judge. So the 365 has realized that they can make things, and if I find them amusing, they still get extra credit over in 365 because I'm a little bit more loose with the meme extra credit than some others, apparently. I specifically did not upvote that one. So it did get upvoted, but it wasn't by me, just because it was too overtly trying to placate me. But for success students, that should be a sign that posting these memes will add up in the long run here. So please do so. All right. Other memes. So we did actually get some memes about the heap and about challenges. One of the things that we start doing in the later half of challenges, apparently in level 13, is we start kind of introducing fake chunks to the heap. And so it is kind of a Trojan horse. I like that meme there on the left hand side. The meme on the right hand side is that terminology being pedantic thing. And depending upon where you read, what you're reading, what you're looking at, and who you talk to, where is the beginning of a chunk is like something people will argue about, right? I believe a chunk includes the metadata that is behind the allocation, which is the usable region that the program, like the region of memory that is intended to be used by the program that's using malloc and free. Some people will disagree, and what makes it even more fun is if you're using something like pwn.debug or Jeff, when they show you the memory addresses, you have to sanity check yourself and say, is the address they're giving me actually a chunk address, or is it the allocated pointer that malloc goes back and forth? Depending upon the plugin, your experience will vary. All right, more memes. This is just kind of a repeat of something we had earlier, which was, do you need to leak it? No, just overwrite it. It's just as good. Over on the right-hand side, this implies that you actually learn stuff from watching these lectures. because you're trying to brute force 16, which is the first level that has safe linking, and it wasn't working. Apparently, you watched the lecture and realized how safe linking works. That's amazing. I think you just really stole my demangle function, but that's totally fine if that was what you needed to solve it. Whoever was the author of that meme. Although I don't think demangle works on 16. At least with the intended approach, it doesn't. So I said meme extra credit and help extra credit is now live. Uh, it is. It just isn't updating. I think I noticed it and one other person did. So Hanto has been just permanently enshrined for the past day in first place with 388 thanks. One thing worth noting is the leaderboard shows repetitive thanks. So if Hanto said something that was like super helpful and 50 people liked it, that's 50 points on the leaderboard. For your course extra credit, it is unique messages, and it does say this on the course page. So one message that is liked by 50 people is worth one thanks as far as the course extra credit is concerned. But do keep in mind it is logarithmic in your favor. So the first two solves are worth 0.89%. I mistakenly said it was like 1 point something prior to starting the stream. And well, it was corrected. You could just get another, you could just say something else that's helpful. Um, so yeah, slow and steady progress here on the dynamic grading stuff. It's moving the right direction. Like nothing is overtly wrong. It just isn't updating, and number isn't going up. I hope to have that fixed realistically Friday, like Friday evening. We'll see if I get to it tonight. I know what it is. I just need to like poke at it a little bit more. Logistical things. So fall break is the 11th to the 14th. Hopefully, I got the dates right. Dang it! So I go to. I'm going to show you what I do. Why this keeps happening. You type ASU academic calendar. You click the first link. You type fall break, and you end up over here. Right? And you see this. But as somebody pointed out, there's a difference between 2024 and 2025. So this year, we'll update the slide. It is the 12th to the 15th. It does not include tomorrow. All right. There will be instructor office hours and recitation, which was something that people were concerned about. However, there will be no class on Tuesday. And there will be no recitations Monday or Tuesday, but there aren't recitations on Tuesday for 466 anyways. As the meme says, you're done with your midterms. It doesn't matter. There's Pwn College. There will always be Pwn College. I told you at the beginning of this course, there's going to be an insane pace and there will always be something assigned, and it's just going to be brutal. You're halfway through it. Accept it. Okay? There is an end to it. It's called the end of the semester. Unless you sign up for more, which would be even more fun. Program exploitation launches tomorrow. I think worth noting about this, it is a cumulative module that's going to cover everything that we talked about so far in the prior material. And so it's going to be taking those concepts like memory corruption, ROP, heap, reverse engineering, etc., and combining these concepts. So you may need to do some memory corruption to then create a scenario where you can ROP. You may need to reverse engineer. You may need to write some shell code in something that isn't x86. I said that Yon 85 makes some appearances multiple times in this material. This is going to be the first return of Yon 85. There are a few twists on some of the existing elements, so there may be some things that were alluded to in earlier material that maybe it wasn't in a challenge, and you'll get to see it or experience it in this combined module because it's more fun if there's more moving pieces. One of the things that people talked about prior to the stream was specifically with the heap is like they were asking a question about how they could generate some leak. And I threw just a couple scenarios at him. I was like, okay, well, you could, do something like the meme on the left here and, inject some fake chunk and then leverage that to obtain a leak. But that isn't something that we like directly present in this material, right? You have to have the intuition that, oh, I have the ability to inject a fake chunk. And I know that fake chunks next are the, if I free another chunk after a fake chunk, the next pointer would be that thing that I freed. And then if I have a use after free, I could like push that, right? I'm not saying that that's the solution to any given challenge, but it's a number of these kind of moving pieces or components, these kind of sub strategies that you can employ. And you have to think about these are all like puzzle pieces. How do I put them together to accomplish what I want to do? A lot of the times, like there are a couple questions on the Discord earlier today where people were saying, "Hey, like I don't know where to go on this challenge." And my first question is, well, what do you know? Like, what do you have? You should always be thinking about these challenges, particularly cumulative type things, with what abilities or powers do I have and what information or facts do I have? Do I have a stack address? Do I have a binary address? Do I have a heap address? Do I have an arbitrary read? Do I have an arbitrary write? Right? You need to start thinking in those terms and what does that mean? What can you do given a set of facts? And what happens is once you state those facts and build up, you find or uncover a path to a more complicated exploitation scenario. There's a reasonably high chance of me adding new challenges to this module in particular. Um, Primarily because there's things that I think should be covered in here that aren't, right? From us shuffling around module material. I'm going to try and hopefully get it included at launch tomorrow. But if I don't, I'm still going to add it. So that's just, it's happening. All right, demo plans. If anyone has anything in particular, you're welcome to hit me. We got one hand. What do we got? That is amazing. All right, what are the next two lines on this slide? What if the pointer gets nulled out? Thinking about overlapping allocations. All right. Every once in a while, I pick a topic that is relevant to what people are thinking about. So I can definitely cover that. And then I'm also going to throw in just some safe linking, mess around with it in a more real scenario instead of just copying random addresses here. We try and include safe linking as part of an exploit. Does anyone have anything else before we kick it off? Yes. Okay. So, okay. So there's a few different things there. It was a straightforward answer until you were like, I read this random thing on Discord and I think this applies. The Discord is great, and then Discord at the same time can be a trap, right? Because I don't, there's limits to like how much I can moderate things, right? As far as how people suggest strategies. So the statement was there's some challenge where I have a leak of I've already managed to leak, for instance, win, and I have a stack address, and so I'm trying to get this value onto the stack. Is that okay? So they're trying to. Are you trying to do like a malloc free? Write the address malloc. Okay. Okay, so you're saying so the question, like the thing that I'm hung up on right now, which is why I can't answer, is what operation is seg faulting? Are you seg faulting on malloc or are you seg faulting on write? Okay, So the statement for Twitch here is they are dealing some safe linking challenge. They're trying to malloc a stack address, I believe, and it turns out that is not going well, and malloc is exploding and seg faulting. So you can malloc one stack address, but not another. Okay. Um, how are you? What is your read primitive? Like, how are you getting bytes into this program? Is it scanf? Is it read? Okay. Um, if it's read, then there's no bad bytes. If it's scanf, because the safe linking are like arbitrarily, not arbitrarily, but XORs your address, right? And it's totally possible, and this is a very real thing, where if you were able to take in bytes via scanf, that the result of safe linking results in a byte that is invalid for scanf, right? So then the address that you're actually writing, because scanf is going to eat and then stop, eat some white space byte, and then it stops, uh, would mean that you're writing an invalid address, which would cause you to segfault on the return. You would also you wouldn't segfault, you'd sig abort. Are you sig aborting or are you segfaulting? I'm sorry? Okay. How have you figured out where you're segfaulting? So, okay. I think I know what's going on now, based on what you've said. Okay, because I was going to say, hey, this is you are not mangling correctly to deal with safe linking, and then you said, hey, I can malloc other stack addresses, and everything's great. All right, and then I thought, okay, well, maybe it's some magic bytes, and scanf is stopping you, and so you're writing an invalid address. You're not writing what you think you're writing. Again, both of these are verifiable in GDB, right? Which is why GDB is amazing. Um, but you say no, it is taking in input via read, so it can't be that there is an invalid byte. So then you say it's a seg fault, it's a seg fault, it's a seg fault. What tool can help you investigate why you're seg faulting? GDB, right? Well, we still ended up with the same place, despite all this reasoning and thinking here. And so we need to figure out why we're seg faulting. Where are we seg faulting? Right. So the seg fault's accessing some invalid memory. malloc itself shouldn't cause like you can seg fault there. But what you'll find is that you're going to be able to attach GDB to your program. You can run it. You'll seg fault. You'll see that you're seg faulting inside probably some like malloc helper function, right? And this malloc helper function is going to have some. It's going to load in some value, and it's going to try and do some math based off of it, and then like load a pointer, right? Dereference a pointer, and that's why you're seg faulting. And so what you need to do is throw GDB at it, figure out what that pointer is, how it relates to what you're trying to allocate, how it's being used, and can you fix it? All right. And it could be that, hey, like envision, I don't have drawing abilities here, but oh, this is not the whatever. For just scratch, we can use this. So imagine I have some pointer that is at 0x1337, right? This is what I'm writing, saved return address. Okay, it's at 1337. Malloc is going to treat this as if it were a valid allocation address, right? And there are some things that we would expect the heap to want to do with something that is a valid allocation pointer. What are some things that the heap might want to do? What might want it to look at? Oh no, so we could malloc, we could free, but what values? A seg fault is we're accessing invalid memory, right? So it could look, it could be looking at 8 bytes before the pointer. What's supposed to be there? My size, right? It may want to look at the size. What else might it want to do? Well, it may look at the size, and then it wants to do what? What happens like when we um, let's think when I malloc something, there is the previous size, right? Where is the previous size located? So okay, that's minus. Okay, we could look at 16 bytes before, because we want to look at the previous size. What else might we want to look at? We might want to look at the next pointer because we're mallocing something, right? And if I'm mallocing, so we might want to look at the value at the pointer because if we're mallocing it and the count is sufficient, this could be a next pointer, right? So the heap could be looking at the pointer or star pointer, right? It could just say, hey, this is the next pointer. I want to dereference it and look ahead. We'd have to look at the malloc source code and see, but that's a reasonable thing that it may want to do because the heap doesn't know that, hey, I'm writing some invalid value here, right? So it's going to assume this is well structured. It could look at not my previous size, but my next chunk's previous size, because that should be the same as my size, right? And that would be pointer plus whatever is at pointer minus 8. It may try and do that. Pointer minus 8 is my size, right? We already saw that. But I may take where I'm at and then look ahead. Technically, it would actually not be that. It'd be this minus 16 because it would be looking for the allocation. Hopefully I'm mathing right, but you see where I'm going there, right? Because where is the previous size of the next chunk? It's at the end of my chunk, right? We think about it as if it's 8 behind or 16 behind me. Another way of looking at it is its size past me is where the next guy's previous size that is mine, right? So any of these things could be happening. And all of these are potential areas of seg faults. And so that's where throwing GDB on it and saying, hey, which one of these memory locations is it looking at? Wow, what is actually causing the seg fault? And is it something that I can fix? Right? It could be any of these. And even once you figure out which one it is, the next question is like, can I fix it? The answer may be yes. At which point, if it's yes, that's great. Then do it, right? What if the answer is no? Okay. If it's no, we could get another leak. Maybe right now you said that you're trying to malloc a saved return address, but I can malloc other stack addresses. Okay. So in earlier challenges, I malloced. Can I malloc something before this because I want to write? Is that correct? Then can I malloc something before? Right? Can I go? How before can I go? Because my goal isn't necessarily to malloc this saved return address. My goal is to set that value. There's a canary in between. Okay. So there's some limitation on how before I can go. Could I leak the canary? Right? At which point, all right, maybe. Now, I think I know, now that we've scribbled all this out, what level this is. What's that? 17. I would have guessed 16. Okay. Um, Now, all of this is presumed, right? Because this is all built on all our whole reasoning is based upon an assumption that you made. And your assumption was that I need to get the heap to malloc my saved return address on the stack. Is that an absolute thing that you must do? Okay, so what if I just don't target that at all? There was a hand. What do we got? Mhm. That has not been freed. I- if it's malloc, well, generally speaking, for Tcache, prev size just doesn't exist. Um, like it's not used. Size would exist, so you could mess around with a malloc chunk size. Such a thing exists. It's not structured in the way that you're phrasing it. Um, so I think I'd rather hit the demo and see if the demo gets you what you need. Um, to wrap up here, there's an assumption that you're making, um, and I don't know that this is a true assumption, right? All of this is predicated on I need malloc to return the saved return address, right? Or something near it, right? And maybe this is true, maybe this isn't. Okay. I know in one of the levels, so maybe 17 is the nasty one. But in one of these levels, this is a specific problem that I like put into this. All right. I apparently I don't necessarily know which level is which by number, where you can't do something direct here. Now there was a hint that you said on the Discord, right? Random man on Discord, random person on Discord says, what did they say? Okay, so that's I'm not quite sure I'm fully following. Okay, all right, okay. So it's a phrasing thing here. So the random person on Discord says, how do these challenges work? We say malloc one, and then some size, and then what happens is there has to be some location, right? There's some array. We'll call it the pointer array, and it is going to be, we'll say 16 in size, right? So there's something like this. And then what's happening when I do this malloc 120 is we're calling malloc 20, and we are saying pointer array 1 equals malloc 20, right? And that makes sense. This isn't like some deep secret. This is something that one of you, any of you, could pretty easily discover by opening up one of these challenges in IDA or Ghidra or whatever your reverse engineering tool is. right? It is expected that you are using IDA Ghidra to look at these challenges, right? The challenges have help text. However, you said 17? All right. However, they can't tell you how everything in this program works, right? You know what does a good job of telling you how a program works? The code or the assembly, the pseudocode, right? And so we're to open this up and we mash tab, very advanced skill here. What do I see here? Right? And IDA thinks it's a void star array of 16. And IDA was nice enough to call it footer. And if we go down and see what happens when you malloc, look, we're indexing into some array. Where is this array located? This array is located on the stack. How else is this array used? We mash X in IDA, so we click on what we're interested in. We hit X for cross-reference, and we can see everywhere that this pointer array is used. Is this something that's interesting to me, and why? Oh, it is pretty interesting to me. We see that that is an argument to puts. We see that's an argument to scanf. We see that's an argument to free. That's an argument to malloc usable size. That's an argument to it's a return value for malloc, right? But it's used in a lot of places. So if I could control that value, does that give me anything? It gives me a lot. It gives me the ability to call puts on it. It gives me the ability to call malloc usable size on it. It gives me the ability to call scanf on it, right? And all I have to do is set what this pointer value is. And so we can bang our head on, I lost my Vim scratch there. We can bang our head on this assumption that I need malloc to return the saved return address, right? And you can fight it and fight it and fight it. Maybe you can and maybe you can't. But the way to move forward is to throw GDB at it, understand why it's failing, how it's failing, and determine is it something that you can fix or is it something that just you cannot address? If it's something you can fix, fix it. If it's something you can't, stop trying to do that. This is an extremely common problem in general, just when you're doing exploitation. Like, hey, I know of this mechanism, I know this trick, I'm going to try it, everything's great, and you just randomly segfault somewhere. In the blue belt material, we have modules where you're doing a lot more fancy pointer stuff, and it's just okay. Well, this pointer is going to get something is going to get offset from here, and it has to be 0. There's another offset from this pointer that you set, and it must be 1. There's another pointer that needs to be a valid pointer that needs to point to something that then gets offset, and that needs to be 12, right? And you just like, okay, I need to make this work. Like that is a very real thing. Now, we aren't going out of our way of doing that in this module, but the sub problem that you're running into is very real, and that is how I would approach it. So the statement was if I can control this pointer value, and the pointer value is used as an argument to scanf, then what do I have? And I think they have realized that that is essentially an arbitrary right, right? I have created an arbitrary right primitive by doing that. And so there's more than one way to skin the cat, as they say. Uh, think about all of the different things that are available to you. It goes back to that kind of statement of facts and building up from there, right? When you start off with a very narrow assumption of like, I need malloc to do this. Okay, that's fine. Is that really your goal? No. My goal is more abstract. And so there may be more than one pathway to accomplish what is truly your goal. Don't get stuck on something. And if you are stuck on something, use GDB or some low-level tool to either rule it in or rule it out, and then move on. All right. So for the slides, I think it was a worthwhile ramble, though. For our demo here, what if the pointer is nulled out, overlapping allocations? What's going on? I'm still going to use the same, see if I can use a keyboard today, same toy binary I have been using, and I still haven't fixed it. But it turns out uh, what I'm going to do is not critical. The bugs that exist in this are not critical. So we've kind of been using this as a straw man for the better part. Well, we'll move do.py to do2.py, and then we'll make a new do.py. All right, so this binary can do all sorts of things, right? But I am going to place some restraints on what I'm going to be able to, how I'm going to be able to use this binary. All right. The first restriction that I'm going to place on myself is I am going to make this binary null itself out. All right. That was one of the kind of rules that the class hit me with here. I don't know that I need the context, but we'll set it. And I can do that on this binary by sending toggle null. All right, cool. It's going to null itself out. The second restriction that I'm going to place on myself is that, which I kind of have already, I have no use after free. Okay. Because it's nulling itself out, there is no use after free. The next thing is I'm not going to give myself an arbitrarily long read, right? We saw earlier that if you have an arbitrarily long scanf, I can just YOLO and write, from one end of the heap to the other if I was so inclined. Instead, I'm going to say that I am allowed to write the allocation size +1. Okay? I'm going to give me +1. We could do 16. Do I need 16? I don't think I need 16 for this. We'll find out. Is that fair? Okay. Um, Now, one of the things that is worth noting that's kind of came up. Oh, no, dang it. Um, okay, I'll say it and then you can tell me if I need to switch levels so I can show this. Uh, what happens if I allocate 32? I call malloc with an argument of 32. How big is the chunk going to be? Okay, the statement was it'll be 32 plus hex 10, which is 16. So 32 plus 16, the chunk will be 48 bytes in size. What happens if I allocate 40 bytes? So the statement was is one of these 8-byte segments will be shared between the two chunks. That's not true. That's not the best way of kind of phrasing it. I wouldn't surprise me if Jan said that, and that's why we use the word share. It's when that chunk is allocated, I own it because it's allocated. But when it's freed, the last 8 bytes of the chunk will hold the previous size, right? And this has an effect that we can clearly observe if we think about this. So if this is chunk 1, we could have 16 bytes here, and then chunk 2, right? The 16 bytes would be prev size, which doesn't really exist, right? And then size. We could have this scenario. And so there's 16 bytes here, right? That's what happens if I allocate something that's a multiple of 16. But if I allocate something that is not a multiple of 16, then I end up with this scenario. Because prev size, we're just going to call it PS, is part of this chunk. Do you agree? Okay. So an effect of that is what is one byte past this allocation. So chunk one PS is the same thing. All right. Uh, it is all my writable area if it's malloc. If it's freed, then there's going to be a next pointer, there's going to be a key thing, there's going to be some space, and then there's going to be a previous size. But what is immediately after my writable area? The size for chunk two. This is a powerful thing to be able to do. I'm going to do it hopefully with one byte. You asked for 16. Hopefully we can do a little bit better. All right. So if I malloc 32 bytes, then what happens is there's 32 bytes here, right? Because that's what I asked for. Behind this will be size, and behind this would be preb size, right? And that's not super important as far as what's going on over here. If I malloc 32 bytes and then malloc 32 bytes, I end up with this setup. So there's 32 bytes, there's 16, this is 32 bytes, this is 8, this is 8, this is 8, 8, and then there's 32. You agree? Cool. What happens if I do 16 plus 8? Well, we're still going to end up with I am going to finish this demo. I'm like committed. Okay. We end up with that same stuff over on this side. But what happens here is the preb size is now shared because it's shared. It is the last 8 bytes of the allocation. And so that means that the distance between the end of the first allocation and the beginning of the next allocation, there's only 8 bytes in between, right? Because since this was 16 plus 8 and it wants to create allocations that end in 0, it's going to solve that problem by reusing the last 8 bytes of the freed allocation for the previous size, because it doesn't matter, it's freed, right? So we'll use that for the previous size. Then we have 8 bytes for the size. Then the chunk starts. And so the number that we choose here will influence what's going on in memory. Does that make sense to everyone in this room? Because it's critical for what I'm going to do. I'm sorry? Yes. So the reason that we have this change is one, for space efficiency, and two, the allocation addresses, which is the beginning of chunk two in both of these diagrams, must have a 0 for the least significant nibble. And so in both of these cases, that happens. All right. go back to our do.py. All right. So let's start making some things. Let's malloc 1. Do I want 32? No. I want 40. I want something that is a multiple of 8 plus 40. I'm going to malloc 2 of them. I don't think I need more than 2 of them for this. I'm going to free 2. I'm going to free. No, I don't want to free. I just want to free 2. Okay. In memory, if we think about my good old diagram here, I'm glad I saved it. Uh, our numbers are corresponding as far as where they are in contiguous memory, as I have diagrammed here, right? I've only freed 2, but in contiguous memory, malloc 2 is in front of malloc 1. I'm allowed the right to malloc 1 because malloc 1 is currently allocated. Everyone agree? Cool. And I had requested 40 bytes. My rules say I can write up to 41. So, what is my read in here? Do I want read? Sure, let's read. Let's read into 1, and I get 41 bytes. All right. Well, what is this doing? I think you see where I'm going. Like I see a slight grin. Well, what's my strategy here? Okay, so the statement was my strategy here, and the reason I need that 1 byte is if I'm allocating something that's 16 plus 8, this is set up to where the first byte, that 1 byte overwrite, is going to overwrite the least significant byte of the size. Now, for this particular just thing, I am doing small allocations, right? But you could envision a scenario where the size is, I don't know, hex 100, right? Or hex 300. Now, if I still only have this 1 byte overwrite, what I'm effectively doing is I'm shrinking the size of this allocation, right? Okay. So how big do we want to make this thing? What do I need to do here? I need A times how many? 40? 40 sounds good. And then we're going to add a byte for the size. I'm going to P8 it. How big do we want to make this bad boy? I don't know. How about F0? Does the 0 matter? So I chose F0 for my size. Does the 0 matter? Should I make this F1 or F8? What are the least significant bits of the size value? Okay, so the statement was if it's 0, then the previous chunk is considered not in use. Yeah, so the flags previous use M mapped for an arena are stored in the least significant bits of this size value. So I'm not just setting a size, but I'm also setting some metadata. I don't think that's going to be immediately relevant here, but it could be. I'm going to do one more thing. We're going to malloc like index 10. I don't know, give me 100 bytes. And all I'm doing is I'm saying that this is the victim chunk. Okay. We will P send line. Let's read something cool into the victim chunk. Let's read in what do we want to read into this thing? P send my secret value. How long is that? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, I believe. So I'm using send, which will not null terminate this. 2, 3, we can just have, yeah, 15. Vim agrees. So that's my victim chunk. Let's do this. And the order of these operations matter. So this is my setup before the victim chunk is malloc. Because what I really need is I need chunk 2 here to be behind my victim chunk. Right? Because the one thing that I could influence in this scenario from overwriting size plus 1 or allocation size plus 1 is the size of chunk 2. Right? And so it's how can I abuse the size of chunk 2 to read chunk 3? That's what I'm going to try and do. I can make, I blew away that free because I think I don't want that free. I can overwrite the size of chunk 2 here to BF0. Is that useful to me? And why? It's useful. All right, we can manipulate the size. So they're both malloc. Let's see if we can use Robert's favorite tool on this. Maybe. See if the old heap works. Oh, I didn't give it. It helps. It helps if you get your shebang right. Um, and from pwn import star. Cool. So that's just chilling there, right? But we did all those operations. We'll find my A dot out. We'll attach GDB. It's 8498. I'm going to do heap bins. Heap bins is not very interesting because I haven't freed anything, right? Heap chunks. Is this going to work? Okay, heap chunks shows me some stuff. If we reference the, oh, there is no, that's a shame. We have no help checks there. Uh, well, let's see if we can reason about this. What did I allocate? Heck, 40? Okay, that's hex 28. Let's do two chunks all. We would expect two chunks to be size 30, but I don't see two chunks that are size 30. Why? Here's one chunk that's size 30. The second one's F0. Right? GDB doesn't know the actual size of the chunk. GDB is using the same metadata the heap is. Where is that victim chunk that I made? I don't I don't see it there, right? How big did I make that thing? My victim chunk is 100. Let's see what the hex of 100 is. I'm looking for something around 64 hex, which would be what? 68 should be like hex 70. It's not happening. Hmm. Why is that? Well, let's take this chunk and let's add F0 to it. How does GDB determine where chunks are? It's using the heap metadata. Everything relies on this heap metadata being correct. So when I corrupted the size value of chunk 2, and we say, hey, Jeff, show me these chunks. It says, yeah, man, you got this chunk. It's size F0. And then when it looks for the next chunk, it literally just takes where we're at and adds F0. And it says, yeah, man, here's the tail. Here's the wilderness, right? So when you corrupt the metadata, particularly these size things, you will break not only the internal representation of the heap, but what these tools are telling you. As far as the heap is concerned, as far as Jeff is concerned, that victim chunk that I allocated, it's part of the chunk too. So that's a interesting scenario. But if I have to follow my rules, I can't just be like, oh, well, I overwrote the size. Therefore, I can write now F1 values, right? That would be cheating, wouldn't it? I need to get what I actually call malloc on. If I call malloc on 40, I'm limited to 40. All right. None of this shenanigans. I'm going to free chunk two. Where's chunk two going to go? It's going to go to the T cache. What bin is it going to go to? The bin that has the bin for 40? We overwrote the size. We made it F0. So it's going to go to the bin that's a correct for F0. Okay. Heap bins. We have one Tcache entry. It is of size F0, and it is that same address that we had. How can I use this to my advantage? F0 is, printed it down here, 240 in decimal. What's that? Well, right now it's this freed chunk. I can only write to things if I malloc it. Those are the rules. Can I malloc that thing? Okay, what do I need to malloc? You want 240? Gonna be wrong. Still there. Why didn't 240 work? There was this great meme slide where I think we were dunking on me, but now I get to turn around and use it to dunk on all of you. The size of the allocation is not the size of the chunk. So what size do I want to allocate? 240 minus 16 is the statement. So let's give that a try. 240 minus 16, 224. I think I can do math today. We'll see if it's a good math day. All right, it's not in the T cache. So we successfully returned that chunk, and I called malloc on 224. So I'm totally allowed to write 224 to it, right? So those were the rules. Okay. So our next question is, well, I wanted to leak this secret value. That's what I wanted to do, right? I don't want to overwrite it. I actually want to leak it this time. It's not a trick. How can I leak it? You want puts? Okay. So there was my puts three. So I got nothing. Sure, there could be null bytes there. There's no reason that there can't be, right? Now, there was a statement from the back that was, hey, we saw something like this before with puts. And our strategy was we put in a whole bunch of bytes up until that location that I'm interested in. Okay. Now, this challenge tells me the address. So I'm going to assume that I have this. We could obtain it from GDB as well, right? Using Jeff Heaps. I don't care about the absolute address. Okay, so it's not critical here. What I'm going to do is I'm going to examine like 200 giant hex at that location. And all I'm looking for is where is this victim chunk? All right, we can see it here, right? This looks like, what is that? 8, 16, 32, 48 bytes in. This starts looking like ASCII. What's this hex 71? The hex 71 is the size of the victim chunk. What we've done is we've created an overlapping allocation scenario. The chunk 3 that I have here starts at exactly the address that I put. And it is, what do we say, 224 bytes in size? So it's pretty big. It's probably most of this. I don't know what's exactly 224 bytes, but we can say that's 16, that's 32, that's 64. That's 64 plus 32. So that's what, 96, right? And then we've already overlapped with our victim chunk because our victim chunk bytes are this right here. This is ASCII. You just have to trust me that it is. And we said we needed to put some printable characters from the beginning of the allocation to where the things I'm interested are. It's going to be 16 times 3, which is what, 48? Cool. So let's finish our exploit here. What do I want to do? Well, we'll read into 3, and I want to read 48. We'll send A times 48. You agree? Last thing I need to do, send line puts on 3. Oh, I don't want to attach. I want to fire off fresh. So close yet so far. What are you mad about? Process has no attribute, percent %s. B equals P, send line, send L. Thank you. It should just be send. What do we see? We leveraged an overlapping allocation and our understanding of how strings work so that when we puts 3, we printed all of these A's and then leaked out a value that was in an allocation we never had control over. Good demo? Answer your question? Nice. Okay. Someone says, time to knit some more core. I don't know. That's probably too hip lingo for me. I don't know what I just said, guys. I apologize. Yes. So the question was, so the reason that this worked is because the third allocation was right next to the second allocation, and that is correct, right? So in my ramble from the very beginning of the week, or very beginning of this module, I said there's 2 things that we're going to be messing around with, right? We're going to be messing around with the metadata and these next pointers and pointers. And the other thing that's relevant is where these chunks are located in memory. What is right next to each other? What I just demoed here was how you can leverage an overlapping chunk, create overlapping chunks based upon where they are located in memory. The reason that it worked is because the order of the mallocs was that 2 is going to be located behind memory or in memory behind my victim chunk. Right. It doesn't matter what size it was, right? It's all breaking off of the wilderness. It's all breaking off of the same region of the heap, right? Now, if imagine that there was something in the T cache that was size 100, how could I deal with that? I'll just malloc some more until it's not, right? Like we can call malloc and free to create the scenario that we need, right? We can exhaust the T cache. We can call malloc 7 times and run the T cache out, right? If these things are out of order, then we malloc and we free and we get rid of stuff until we make it the order that we want. Nothing in this module goes like too crazy with creating specific states of the heap, but in more advanced heap exploitation, that is 100% what you do because you care about the proximity of one chunk to another, generally speaking, a chunk you control, and then a victim chunk. How are they located next to each other in memory? And so sometimes it's not even something that you can deterministically do. Like if you not relevant to this module, but like kernel heap exploitation, you end up doing things where it's statistically likely that this could occur. But the general logic of creating a chunk that you can control and then a victim chunk and having them near each other is 100% a consistent theme and something that you should internalize. So I didn't get time to use safe linking, but that's a-okay because all I was going to do was use this exact same binary, or not this exact same binary, but this exact same exploit, except use the binary that had safe linking. And you know what we'd have to do to it? Okay, the statement was demangle and protect it. What did I call this thing? Do.py, and I have safe linking dot out. Well, let's find out together. I didn't test this. Ah, nothing. Why? I'm not corrupting any pointers. I'm corrupting the size. At no point am I trying to malloc a user controlled data. And this is what I mean when I say safe linking is a pain in some cases, and it does absolutely nothing in others. Think about the details of what is actually occurring. At no point did safe linking that I did have to change anything to make this exploit work with safe linking. In other scenarios where we do care about next pointers and trying to generate stuff or leak stuff, safe linking will be ever present in a giant pain. All right. Twitch, you were pretty quiet today. That's a-okay to me. It's fall break. I'm going to try and enjoy it myself. I want to say I hope you guys will too. Um, at least finish the heap stuff. I'll give you that. Like I don't think the heap stuff's too bad. All right. I will come back and look at the equivalent of a pwn.college midterm since you're done with the rest of them. I should have your full attention, right? All right. I'll see you guys next week.